Hello, everyone. My name is Victor Diaz. I come from Cal Poly Humboldt. And here at UT Dallas, my research focus on augmenting deception detection through the use of machine learning and exclusive use of visual features. Before we talk about any machine learning aspect, we need to know what deception is, how do we detect it, kind of these key ideas before we even get into any of the machine learning processes. So what is deception? Deception is trying to make someone believe in something that you know not to be true. Right? An example is going to be think of a fruit, an orange, you knowing that the fruit you're holding is an orange and trying to convince someone that it's an apple. So you knowing the thing is not what you're trying to express. That's like a basic form of deception. Now, if you think the object you're holding is to be true, it's the truth. There's no deceptive behavior behind it, and there's no deception behind that, like those types of statements. Now that we know what deception is, how do we detect it, right? So generally speaking, studies have shown that there are measurable abnormalities when lying or deceiving. When these actions occur, there are certain abnormalities that we can look at, right? Think of a polygraph test. Now, in a polygraph test, you're measured when you're telling the truth, and then you get asked a series of questions, and we can see when a person is out of the certain range of normal, right? So there's been a lot of issues where we don't know exactly, not one exact measurement is lying, but what lying can be measured is when you are out of your normal range of speaking or out of your normal range of behaviors. All right, so now we know what deception is. All right, so what are some of the issues in deception detection? So one of the most prominent issues in deception is the lack of diagnostical cues. So what this means is the human body is too complex, and we haven't looked at every single type of hue that there is. Okay, so imagine your eyes. Just look how complex your eye is, and we haven't looked at if your pupil dilates at a certain percentage, or if you blink too many times, or you blink a certain rate. The diagnostical cues, the research in this area is very limited because of how complex the human body is, right? We have so many neurons and so many just movements that we don't know. Like think about your face, how complicated your face is, how many muscles you have, all the twitches. If we would like more diagnostic cues, like what if something we don't know is if your eyebrow twitches or etc. There hasn't been enough work done in this type of research in this area. Now, the second big issue is specialized research in the methodology. So again, because the human body is so complex, there's been general schematics looked at, whereas you see hand movement, like how hand movement affects, or breathing, or like a polygraph test. But because controlling the whole human body cognitively is very hard to look at, we can't control every single action of every single methodology, right? So if we're looking at heart rate, controlling the heart rate at a specific time is very hard. So research into the methodology has like limits the work that we can do, because humans can only do so much work, and we can only look at so many things, which there's still so much work to be done in deception work. So here's where my research at UT Dallas kind of partakes, is implementing machine learning in deception work. So the main issue with, or the main couple of issues with deception work, is a lack of cues and a lack of specialization in the research, or the lack of specialization in the methodology. Now, machine learning can tackle these problems very, very well. So with a deep neural network and deep learning, we can take the biggest issue of diagnostical cues. So while we humans may not be able to identify every single aspect of a face and how a face twitches and how a face moves, if we're able to feed this type of information into a deep learning algorithm will learn, or will hopefully will find these patterns in deception work and in truth telling. That's the whole idea between deep learning. You feed it a bunch of information and it will find patterns by itself. So deep learning can really address the issue of diagnostic cues by feeding it enough information. It should find cues that are kind of very hard to tell by the human eye. Now, specialized research in the methodology, that's kind of a very nice thing we can tackle with extensive testing. So like the difference between normal testing technology and testing with the AI model is in an AI model, you can constantly test it, constantly. Once you have the information processed into your computer and it's in the model, adding new information is never a problem, and keeping it all controlled once you have it all is very simple, because you can constantly try different models and try different approaches. So once you have the data, researching it through methodology becomes like a simple part of machine learning. And we can also use single modality. In this research, we use specifically visual features. But with machine learning and this type of kind of work, you can focus on only voice, only visual inputs, only hand movements, only certain kind of information. As long as you can track it and feed it into a model, with machine learning, you can definitely address these two issues, which have been present in deception work. All right, so we know what deception is. We know how that it is possible to classify, and we see the benefits of machine learning, how machine learning can address kind of these really big issues that we see right now. But what is machine learning and what aspect are we going to use? So we are going to be using machine learning classification, which the primary goal is to classify an object from previously trained data. So the whole goal with a machine learning algorithm for deception work would be to predict, once a video is fed, would be to predict if this is deceptual kind of behavior or if it's truth-telling behavior. That's the whole goal with this approach. Now, basic schematics for machine learning would be: you collect data, you process the data, you select some features that you would like to look at, you select the correct model, you train the model, and then you evaluate it. So this all will depend on what you're looking at. It varies if you're looking at kind of language or text-based stuff, images. Really depends on what you're looking at. Since this study focused mainly on visual features, we will be looking at image recognition. So our model selection will be something that deals with images or videos, because our data are video files from deception. So our whole machine learning will focus on the aspect of images. All right, since we already said that we're dealing with imagery and visual analysis, we will be using a convolutional neural network. A convolutional neural network specializes in visual imagery, and it deals with this type of information because it will always depend on what information you have available. And since we would like visual information from video cameras, a convolutional neural network, it's the perfect way of, or the perfect model kind of architect that we want to use. So a convolutional neural network will take an image like we see here, then it will break it up into sections, and then zoom that image in, break it up again, and be looking for patterns and be looking for anything that the deep neural network thinks or sees in common with all its information that is deception work. Here's a kind of a little short diagram of how it works. At the end, it has a neural network of information that knows that this is deceptional work or truth telling, which would be our two labels that we see here. The next model we're going to use that kind of adds on to the deep neural network is a media pipe holistic landmarker. So this fills in the gap that a deep neural network kind of has, or that a deep neural network will make when dealing with this type of imagery and this type of information. What the goal of the MetaPipe holistic landmarker is to fully track the human body. So as you can see here from the images, the landmarker analyzes the full body face. So it keeps information on faces, keeps information on hands, and keeps information on the whole body. And this just cleans up the data for a classifier later to be used. So with a deep neural network that can find and identify features and the holistic landmark, we can map kind of the whole body. That's what this approach was. And many studies have shown that tracking deception work with hands or movement of the body is generally a good sign or a more progressive sign towards the work. This is why we are adding on the holistic landmarker to track everything, to give a full scope of the whole body, whole person when they're deceiving. So in this research, we propose this multimodal model. Multimodal models just kind of means that we have different avenues for extracting information. The first two, the 3D CNN feature extraction and the LSTM feature extraction, those two are deep neural convolutional networks, which work like the way explained before, which will take information, take frames, take video data, scan them themselves, and then come out with a decision output, as you can see here. So all these are independent models that come up with the decision by themselves. And the holistic landmark extraction, same way. It will find features, identify them. We're going to aggregate them just to make them look all pretty, and there will be a decision output. Then combining all three and looking at all three data points, we will make a classification based on a random forest tree, which will be created from these three sections. So this is the proposed model. We're taking in video inputs and feeding them into two deep neural networks, and then taking information from the holistic landmark extractions and creating a decision tree based on all this. So now we know what deception is. Now we know that deception can be classified. We know the issues and how machine learning can address some of those issues, and our proposed classifier model. So now it's time for the experiment and building the whole model. So for this experiment and the training system, we use 121 real-life trial-based videos, which the labeling comes from looking at the judge's decision, later interviews, and the whole frame to identify if someone was lying when taking the video or if they were telling the truth. So from that, we split it up into two sections: our training section, which we will train the model for, and our testing section, which the model will never look at. This information is kept private so that later on, when we test the model, we have some clean information that is similar in input, but that the model has never seen to classify it. So again, machine learning It all depends on the inputs. It all depends how well you clean the data. So we have 48 videos, 48 truth videos and 49 deception videos. How do we clean them up? How do we make them pretty to feed into a model? So we take the 100, we take the 99, we take the 97 videos for training. We take those, split them up into 64 set frames using OpenCV. Then we capture the faces using OpenCV. And then we have a total training set of 493 videos for truth and 534 videos for deception. And we have a test set of 121 and 138. So just by processing the data a little differently, we take the 120 videos and we expand them to be able to really train our model correctly. So now we have a proposed model and we've trained it. We built the proposed model, we've trained it. How do we know how good it is, how correct, what its accuracy, and how do we test it? How we know that every step we added correct features, we're doing a kind of a better job. So we create different test sets to simulate kind of what real life would look like if we were to send this model out into the world. So we have a raw test set, which is composed of just 12, the original 12 videos that we extracted from the beginning, which are 12 truth videos and our 12 deception videos. Now, these are unprocessed raw videos that if you were to take from a Zoom call or like this video, if you just pull it from the internet and fit it into the model, not fixing anything from it. This is a raw test set. Our training set of 64 frames are, if you would take the test set and process them the same way we cleaned out a lot of information, creating 64 frame sets. It requires a little processing, but kind of just to get an idea of how our model can do with different types of information. And then we have our split test set, which is where we took our training set and split that from our original one to get the 99 videos and the 110 videos. The split test set, the model has seen similar videos before, so the people, I would say, are the same. So the model has an idea. The split test set, the model has an idea of these people and has looked at them. This information is not completely foreign. It can recognize the people and it can recognize how not only the process, how the data is processed, but also the people inside it. So it remembers a lot more. So that's our test set. And then at every step, we have models and we will test them against each other to see which one is correct. This is our final results table. So a little more explanation on how we tested it, I guess. So the single models you see here are the ones in purple, red, green. So at every step, every decision tree has an output. So we checked every single modality, then we did some different combinations of them, and tested it at the end against our proposed model. So ironically, our proposed model did not do as good as we liked. Actually, the model that performed the best on the raw test set and the sets of frames are the two deep learning multimodal. So when you would combine 3D-CNN feature extraction and LSTM feature extraction, when you combine these two together, that deep learning framework did the best. When you leave all the training up to the computer and figuring it all out up to a deep neural network, that did the best to our just raw tested our new information. When we added, so here we have the 3D-CNN, when we added the holistic landmark classification and our random forest tree classifier, the percentage went down about 5%, which is pretty, I guess, significant, which is nice, but we did prove, or we did have the conclusion of, if you were to have a more deep neural network action in deception work, the possibilities could do a lot better. So this information was done with all its visual features, which research has shown, which is very tough to classify with by itself. And for future work, I would suggest looking a lot more into multi-models, deep learning with a lot more models. So looking at language and visual and any information you can get. So the more diverse set we can find for deception work, the better. Just really cleaning up the data. For the splits test, I know that our other neural network did 91, but this all comes from the limitations from this study really come from parameter tuning of the model and rechecking it, which isn't one of my specialties. So that's a limitation from the model. This is probably done from overtraining the model on specific data. And yes, so thank you very much for listening to my presentation. I hope you guys have a wonderful day. If you have any questions, feel free to email me. Thank you very much.